All right, good morning, everyone. So let's continue on our discussion of the first unit, which is simple linear regression. So this slide here kind of summarizes the situation. We have a data set, which is described by these points here. In this case, our data set is simple. The points are just pairs of xi, yi. Our goal is to predict yi, or to predict a new value of y from a new value of x. So we postulate this very simple model, which is that y is approximately a scaled value of x plus an offset. And if we hypothesize a particular pair of beta 0, beta 1 coefficients, that gives us a line somewhere here. So our goal is to figure out what are those beta 0, beta 1 coefficients that best fit the data we've collected. So in this picture, the line here looks like a very good match. So how did we come up with those coefficients? So first of all, just some terminology. We define y hat as the predicted value of y. So this expression here, this is exactly y hat. Now, our y hat is not exactly equal to the true y, so we have an approximate equal sign there. Another way we can write the true y is with y hat plus a residual called epsilon, and the residual is just there to acknowledge the difference between our model and the actual data, which in this figure would be just the vertical distance between the points and the line. So that's the setup. That's what we're doing. And our objective is to figure out exactly what these coefficients are. So there's different ways of doing this, but we're going to choose. Okay, so in general, we want to make y hat close to yi, or y hat close to y. So we're going to do this by minimizing or penalizing the sum squared difference over our data set. Sum squared difference between y hat and yi. That's equivalent to the sum squared residuals. So we call this residual sum of squares, RSS, and that's what we'd like to minimize. So we want to find the beta coefficients that minimize that. So last time, so that's our objective. Now, we're going to do a derivation to figure out what exactly those betas are, but to help make that derivation more meaningful and a little bit more concise, we took a slight detour and we talked about some basic statistics that we can use to describe data. And they're summarized in this table over here. Here we go. So we have the sample mean, call that x bar, and that's just the average value of samples in a set, or you can think of it as a vector. We have the sample variance. That is going to be the average deviation between xi and its mean value, sample mean squared. We call that either sxx or sx squared. The sample standard deviation is just simply the square root of that. The sample covariance is this quantity here. It's the average product of xi minus its mean and yi minus its mean. And then we have a normalized version of that called the sample correlation coefficient, which is just sxy divided by sx and sy. And the sample correlation coefficient, if you remember, the reason why it really helps to normalize it is that the final value is guaranteed to be between 1 and minus 1. And now there's a lot of interpretation. When the value is 1, then x and y lie perfectly on a line that has a positive slope. When y equals -1, they lie on a line that has a negative slope. And values in between mean that they're not on a line, they're more of a cloud shape. And the closer you get to 0, the fatter that cloud is. Okay, so that's just to kind of review where we were at the end of the last lecture. And now we can turn our attention to minimizing the RSS. So the first thing we noticed is that if we want to try to visualize the problem, this RSS is, so number one, it's a quadratic function of the betas. And because it's a quadratic function, it has this particular shape. It looks like a parabola in 2 dimensions, or a paraboloid. And in particular, that paraboloid is pointing up. So it has a minimum. And that minimum we can find by searching for the values of beta 1 and beta 0 where the derivatives of the RSS equal 0 in any direction. So if I'm right at the bottom, somewhere over there, and I look in any direction, I would find that my slope is 0. And we can formalize that by saying that the partial derivative of RSS with respect to beta 0 equals 0, and the partial derivative of RSS with respect to beta 1 equals 0. And so it's actually by solving this system of equations that we can find out exactly what the minimizing values of beta 0 and beta 1 are. So we're going to do that. We're going to do that on the next couple pages. But let me just summarize what they are right now. So we have the beta 1 is going to be SXY over SXX. There's another way of writing that. We can write that in terms of the row XY by multiplying that times SY over SX. And beta 0 is going to be Y bar minus beta 1 X bar. So again, we're going to derive this in the next couple pages, but this is, as we'll see, what the answer is going to be. A couple of things to note just by looking at these equations. If I scale my data set, if I scale both x and y by the same amount, does beta 1 change? If I make x, all my x's twice as big, all my y's twice as big? No, right? Because both the numerator and denominator would scale equally and then we cancel out. What about beta 0? If I scaled x and y by a factor of 2, what would happen to beta 0? It would also increase by a factor of 2, right? Because this would double, and we said that this stays the same. Okay, so just by looking at these equations, you can get kind of a sense of what these coefficients are saying to us. Okay, so now let's do the derivation. So as we said, we want to find the values beta 0 and beta 1 that zero the gradient vector. They zero those two partial derivatives. So let's just start out. So first of all, we want to take the partial derivative of RSS with respect to beta naught. So let's remember what that is. We have the partial derivative, and then we have the sum I equals 1 to n, and then RSS was yi minus yi hat, but let's write yi hat explicitly in terms of the betas. So we're going to have beta 0 minus beta 1 xi squared. So now let's carry out this partial differentiation. So we're going to use the chain rule. And first, the chain rule tells us we'll bring the 2 down, and then we'll differentiate what's inside that square with respect to beta naught, and you can see the derivative of that will be minus 1. So if we summarize all that, we're going to have minus 2 times the sum of yi minus beta 0 minus beta 1 xi. Okay, any questions on that? Okay, so we're going to do the same thing again, but we're going to take the derivative with respect to beta 1. So I'll just rewrite this so we can stare at it again. All right, so here again, we're going to use the chain rule. So that means the 2 will come down. But now when I take the derivative of the interior here, I can see derivative with respect to beta 1 is going to be minus xi. So that minus xi is going to come out as well. So I'm going to have minus 2, like before. I'm going to have my sum. And then I'm going to have xi times that interior stuff. Okay, so those are these two equations. We have to do a little bit more work to set them simultaneously to 0. It's not too bad, but we have a little more work to do. Any questions so far? Okay, so what we're going to do is we're going to leverage some of those statistical expressions that we established at the end of the last lecture. And so what we can do, first of all, in order to facilitate that, if we multiply both sides by minus 1 over 2n, that will cancel the minus 2. It'll actually turn the minus 2 into a 1 over n, right? And once it's a 1 over n, then all of a sudden, I think some expressions will pop out. So for example, the first one we see is this. And we can recognize that right away as the sample mean of y, which we call y bar. Okay, the second thing is we're going to have the average of minus beta 0, which is just minus beta 0. Then we'll have the average of minus beta 1 x1. So we're going to have the minus beta 1, and then that gives what remains is the average of xi. And the average of xi here, we call that x bar. So that's pretty straightforward. And finally, so 0 equals y bar minus beta 0 times beta 1x. We can rearrange that into the equation beta 0 equals y bar minus beta 1 x bar. And this is actually, if you remember, this is the expression for the optimal beta 0 expressed in terms of sample means of y and x and the optimal beta 1. We don't yet know what the optimal beta 1 is, but once we do know what it is, then we can plug it into this equation and we'll be done. Okay, any questions so far? All right, so let's do the same to equation 2 here. We're going to multiply this by minus 1 over 2n, which turns this minus 2 into 1 over n. And then we have this equation here. And now just distributing this average, so we're going to have the average of xi, yi. Then we're going to have this times minus beta naught, which is just minus x bar beta naught. And finally, we'll have this times this over here. So we're going to have this term. This is going to be the average of xi squared. Now, if you remember, we derived some useful expressions for the average of xy squared and the average of xi yi. We were able to write those things in terms of the variances and the sample means. And so in particular, okay, so let's, before we even do that, let's plug this expression here into here. So that's going to give us x bar y bar, and we're going to have an x bar squared beta 1 and beta 0. So let's see. So we're going to have this expression here after we plug in the beta 0 term. And now, if you remember, this expression is the one we derived for rho xy. Sorry, sxy. xy. And the one on the right is an expression for sxx. So putting these things together, we can immediately see that beta 1 must equal sxy over sxx. Okay, so that's where we got those two equations for the RSS minimizing coefficients. These are the ones that set the derivatives to 0, which are the ones at the bottom of the bowl. Okay, any questions on derivation? Anything good so far? Okay. So one last thing. Let's find the minimum value of the RSS. In other words, the height of the bottom of the bowl. We found the location, let's find the height. So what we have to do is we just have to take our expression, which we started by writing like this, and we just plug in our two values that we just derived. So plugging in beta 0, remember beta 0 is y bar minus beta 1 x bar. That gives us this expression. And before we plug in beta 1, let's expand this quadratic. So we're going to get the first term squared, we're going to get the cross terms, and then we're going to get the second term squared. So here's the first term squared, here's the cross terms, and here's the second term squared. When we look at that first term, what do we recognize that as? Does anybody remember? Yeah, this is the variance of y, right? So you can call it SYY. What about this middle bracket term? Yeah, that's the, oh, actually, sorry, there's also an n because we're missing the 1 over n in front of the sum. So this is actually n times SYY and n times SXY. And finally, the right bracket, n times SXX. Okay, so now we're ready to plug in the value beta 1 here, and then as you'll see, the expression will all be in terms of SYYs, SXXs, and SXYs. And in particular, so this first one gives us this. If I plug this into here and combine with the rest, I get this. I basically get SXY squared divided by SX times minus 2. And then the last one, I have plugged this into here, so I'm going to get SXY squared, and then we're going to get divided by SX squared times SX. So I'm going to get this. So as you can see, these two last terms can be combined into this, and if we want, we can pull out an SYY to the outside, because this might give us something. Does anybody recognize what this term is here? This is the rho xy squared. So we get n times 1 minus rho xy squared times SYY. Okay, so this is the minimum value of RSS. So knowing what we know about rho xy, what's something that you can immediately see? What if the xy pairs perfectly lie on a straight line? What does that mean in terms of rho xy? What did we say? When they lie on a straight line, rho xy equals either 1 or minus 1, right? So in either of those cases, what happens here? What does this turn into? 0. That means RSS is 0, right? That makes sense, because if things are perfectly on a line, that means I can fit them perfectly with a line and get 0 error. So just what we expect. The other things we notice about this RSS expression is that it grows with n. That makes sense because it's just the sum of all the errors. So the larger our data set, the more things we're adding, so it grows linearly with n. And finally, it's also proportional to SYY, the variance of y. So the larger our targets are, the larger our RSS is. So those are all the things we can see looking at this expression. But really the most important thing tells us that the closer, the smaller the correlation coefficient is, meaning the closer you can put XY on a line, the smaller your RSS will be, and that's very intuitive. All right, any questions on anything on this page? Okay, so we now have our equations. We can return to our automobile demo where we're predicting miles per gallon from horsepower. This is our data set. We can compute the mean. So this is NumPy mean. It just takes that vector x and averages the values in it. And then we're doing NumPy mean on here the difference between x and its mean squared. That gives it SXX. And then we have similarly SYY. And then even similarly again, we can make the vector y minus its mean, multiply pointwise times the vector x minus its mean, and take the mean of that. That gives us SXY or SYX. And finally, we can apply the two equations we just derived to get beta 1 and beta 0. We happen to get these values, 39.94 minus 0.016. Because beta 1 is negative, the line is sloping down. In any case, our model is as follows. Our estimate of miles per gallon is beta 0 plus beta 1 times horsepower for these beta values. So that's where we get this. So that's just a relatively simple demonstration of what we can do with simple linear regression. We call it simple linear regression because it involves one predictor, one feature. In the next unit, we're going to use multiple features, and we'll just call that multiple linear regression. If you want to see another good demo, you can find one at this link. All right, any questions so far? All right, so one last thing to do is assessing the goodness of fit. Whenever you do this kind of fit on a data set, you want to ask yourself the question, did it work, or is this a really bad fit to the data set? We want to quantify that. So that's our objective now, how to judge whether a predictor is doing well in a data set. So in a nutshell, we're going to use a normalized version of RSS. And as we talked about before, RSS scales with the number of samples, and it also scales with the variance of y. Both of those things kind of hinder our ability to interpret RSS. So if we divide by the, for example, if we divide RSS by n, now this normalized RSS is no longer a function of n, and it doesn't depend on how big our data set is. That's useful. Similarly, if we take that normalized thing and we also divide by the variance of y, we get a new quantity which is not dependent on the scale of y nor on the sample, on the number of samples. And this final normalized RSS is very interpretable. So traditionally, instead of reporting that quantity, you report 1 minus that quantity. So 1 minus RSS divided by n divided by sy squared. And this is given the name, or the variable r squared. It's known as the coefficient of determination. There's kind of a longer explanation for exactly what that term means, coefficient of determination, and I'm not going to get into it in this class, but if you're curious, you can click on this Wikipedia link here. But let's just focus on interpreting this value of r squared. So let's first of all think, what happens if I have perfect prediction? So perfect prediction means RSS is what? 0, right? And if RSS is 0, this term goes to 0 and r squared becomes 1. Okay, so whenever you see r squared is 1, that means perfect prediction. Can you get higher than 1? It's impossible, right? Because to get higher than 1, I would have to make RSS negative, and RSS is sum of squares. It's impossible. It can never be negative. Okay, so r squared is 1 is the best you can do. So if you get close to 1 for your RSS, you're very happy. Well, let's talk about it the other way. What happens if I have a trivial estimator that I create this way? I just set every y hat I set that to the sample mean. So in other words, to do that, I don't even have to look at the feature x at all, right? I ignore x completely. I just look at the targets and I just say, I'm predicting a new target as the average of all the targets I've seen. I would say that's a trivial predictor. So let's look at RSS again. RSS is, sorry, there's no 1 over. It's just the sum of y hat, or so let's say yi minus y hat, right? Now imagine that y hat is y bar. What's another name for this RSS? So plug in y bar here. What is this quantity? It's one of the statistics that we've derived or defined. Should be easy. What's the sum? Oops. What's the sum of the square of yi minus its mean? Yeah, n times s by y, right? Or sy squared. So if RSS is that value, and you plug this value into here, you divide by the n, you divide by the sy squared, this thing turns into 1. And r squared turns into 0. So this is another useful reference. R squared equals 0. It means the predictor that you've designed is no better than the trivial one, which could have been designed by completely ignoring x altogether. That's not much prediction if you're ignoring the predictor. Okay? So in almost all cases, you hope that, well, you always hope that r squared is between 0 and 1. Is it possible to have r squared be negative? Some people are saying no. Does anybody think yes? Okay, so if you find r squared negative, it can go negative if all that's required is for this to be greater than 1. And that can happen, number one, if you make a mistake in your coding, okay? And you notice r squared is greater than 1, r squared is less than 0, you say, oh, okay, I must have made an error somewhere. Something is wrong. I guess if you find that r squared is greater than 1, that would also be a sign that there's an error. But just be aware that, yes, r squared less than 0 can exist. It just means that the estimator you've designed or implemented is worse than the trivial one. So watch out. You can do better. Okay. Let me also just say one other note here. So far we've focused on the training data alone. Let's say that there's also another data set that we haven't touched. We'll call it test data for now. And we've designed our predictor on the training data. We know that the r squared behaves this way. What if I take that same predictor and then apply it to this data I've never seen before? And I find that r squared is negative. Should that surprise me? Maybe not, because as we'll see, it's possible to do really well on the data you're given and then still do poorly on new data that you have not seen before. We'll talk about that in Unit 3, but the reason I'm pointing this out is that if you see negative RSS on your training set, that's a flag that you've made a mistake. But if you see negative RSS in your test set, that means that maybe you didn't make a mistake, but it's just that what you've designed on the training is not generalizing to the test. So we'll talk a lot more about that in a couple weeks, but just wanted to point that out quickly. Because in your labs, you will start to compute RSS, and then these issues might come up. Okay, so let's see. So the very last thing is, okay, what about our least squares coefficients? If we have the optimal betas, we have derived an RSS of exactly this. N times 1 minus rho squared xy times sy squared. If I plug this expression into here, then I find that the r squared, as you can see, it's going to divide by n and sy squared, so those are gone. And it's going to take 1 minus the remaining thing, and finally at the end of the day, we find that r squared is rho xy squared. Simple as that. Okay, so if you use the least squares betas, your r squared is just no more than rho xy squared. So that rho xy really tells you everything about the linear predictability of your data. When rho xy is close to 1, great. You can do quite well with the linear predictor. As rho xy gets close to 0, worse and worse. And once rho xy is exactly 0, which can happen, that means linear prediction doesn't do anything really. It's trivial. It's as good as trivial. You can't do anything with x to predict y. Yes?
So is that only the case when we use the optimal beta, not the beta one? Because then we could get a negative r squared, right? Because rho is between negative 1 and 1. And
Oh, but notice that there's a square here.
right.
So even if rho xy is negative, the square will make it positive.
Right, so it couldn't be less than 0 r squared.
That's exactly right. If you use the least squares coefficients, you can never get r squared less than 0. And that's why I was saying if you have in your implementation, you've made a mistake. Especially for the least squares coefficients, definitely yes. But it is possible to design really bad coefficients, right? Like I can go here and I can design my beta this way to give that line, and then that's going to be probably a negative r squared. So certainly is it possible, but least squares would never do that. Okay, great. So finally, just to finish up, let's visualize a little bit more about this. Yeah.
But if the normal sample is increasing, the r squared is also increasing always.
Can you say that again? If what is increasing?
R squared is increasing always by increasing the n. Doesn't it like that?
No. So the r.
Take the points, then r squared will increase.
So the RSS. This increases with n, and so by dividing n, we remove the dependence on n altogether.
Thinking is the square of sy. If you have more data points, then this is something that the denominator is increasing. And
Which are you talking about this?
yeah,
Okay, so we have RSS here, we're dividing by n, and then we're dividing by sy squared. Right, so if we look at the expression for RSS, we see that we are removing this and we are removing this, and that all is left is this. So we divide by n in the r squared precisely to get rid of this n dependence. We divide by sy squared to get rid of this. So what we have left is this, and as we know, rho xy is bounded between 1 and minus 1 for any n. Does that answer your question? Okay.
The thing associated with increasing the sample size is that the improvement in the significance of the confidence that you get. So you like the more sample you have, I guess the more confident, statistically confident you will be in terms of your prediction. But that doesn't have to do anything with the.
Yeah, that's not really going on right now. We will talk about that idea in Unit 3. We'll talk about those ideas, the accuracy of sample variance, whether it's asymptotically correct and so on, but none of that is happening right now. Okay, so let's visualize this rho xy squared from our data, because we know that rho xy squared is just r squared if we do the least squares fit. And let's try to visualize some different data sets. So if this is 1, close to 1, least squares gives a very good fit. If it's close to 0, least squares gives a very poor fit. And finally, one other thing. Since the least squares coefficient is this beta 1, where rho can be positive or negative, we know that the sine of beta 1 is always going to be equal to the sine of rho xy. So here is some pictures. This is the same one we saw before of data scatter plots with varying rho xy. So positive over here, negative over here. You can see starts on a line on the edges. As you move towards the center, the line fattens. When you're at 0, you have a cloud that is more or less circular. There's no way that I can fit a line in any direction to get any kind of good fit. And in this case, my prediction, my least squares predictor would say just ignore x altogether. Just use the mean of y. Okay, now let's focus on this case of rho xy at the extremes, either 1 or -1. These are all examples of that. So this line does not need to be at 45 degrees. You could have a line at any slope, as long as the slope is not 0. And so all these guys would be rho xy is 1. All these are rho xy is -1 because of the negative slope. And finally, these are all interesting examples where the data set has rho xy equals 0. So as you can see, it does not have to be circular. Circular is one way to do it, but there's actually all sorts of other ways to get data that has no correlation between x and y. So a ring, 4 clouds like this, these shapes, even a tilted square, all these guys give rho xy equals 0. So the point is that all of these would not be things that we could fit with a linear model. Now, when you look at these, you can see a lot of structure. So it's not that there's no structure in the data and we can't do machine learning with it. It's just that linear models are too weak to do anything with these data sets. And that motivates us as we go through the semester. We will do more and more sophisticated things. We'll move away from linear to nonlinear. And that's our objective, is to deal with real-world data sets that are not easily modeled with linear models.
I'm curious about the second one. Is there any example of any pattern where the second row, an example of any pattern that will be parallel with the y-axis? Close to infinite.
That would mean that that in your data set, x always takes one value, and that y always has, y has like any values. So that would be definitely a pathological case. yeah, you would actually get y would be infinite variance, and so hopefully you don't encounter that data set. Okay, so let's continue this. So when you try your linear fit and you don't get a good fit, you can often, at least these pictures give us some intuition about why that is. There's actually many reasons why you might not get a great fit from a linear model. So one example would be this. So it looks like, in this case, a linear model might do just as well as any model, but it's just that the data has some independent error that deviates from a linear model. So here I would say a linear model is a good thing to do, although the performance is not perfect. Moving on to this one, you can see that the data is very structured and that I could do better with another model. Linear model is not doing well because that model is too weak. We'll talk about this more later in terms of bias and variance and so on, but here it is possible to do much better if I had some sort of nonlinear model. What about this case? So here, it looks like, with the exception of this one data sample, the rest of the data is linear. So now, there might be various reasons for why that data sample is up there. This could be some sort of mistake almost, or what we call an outlier, or something where there was, this is not truly there in reality. It was just somehow our data collection got corrupted. Now, on the other hand, we don't know that because this is all we're given, so maybe in reality there is this spike there. Who knows? And then here's another very weird case where we're only given two different values of x, and one of them has quite a range and the other doesn't. So this, I would say, is going to be a pretty difficult situation. I don't know that you could really do any better than a linear model in this case, but this is kind of a weird case. So there's all sorts of reasons why linear models might not be working well, and generally speaking, you have to look closer at your data to figure that out. Okay, and the very last thing is, even though linear models seem to be kind of weak, you are allowed to do some nonlinear pre-processing to your data, get a new data set, and then apply a linear model to that new data set. And that idea is actually extremely powerful. And let me just show you one example. So until now, we've been predicting miles per gallon from horsepower, and this is the least squares linear fit in orange that we came up with. And as you can see, it doesn't do a great job. What if instead of predicting miles per gallon from horsepower, I chose to predict 1 over miles per gallon from horsepower? So now I have kind of redefined my data. I've just inverted my labels, my targets, but I'm still doing a linear fit on this new data set. So what's nice about that is I can apply everything I know about linear regression, I can apply to this. And as you can see, I'm motivated to do this in this particular example because the new data set I get, which is 1 over miles per gallon here, actually looks quite linear, right? So if what I do is I do a linear fit here, let's say that I get a model that looks something like this, and then I do a 1 over this model, so I get, so whatever this model is, it's predicting 1 over miles per gallon, so I just invert it. As a result of doing that, I will get this green line. And now, so I'm plotting that the model that's linear in this space becomes nonlinear here, and it fits my data quite well. But the point is that I have used all my linear prediction, all those derivations and everything, I get to use them again in this case. So the point is that even though linear models seem to be pretty simple. If you allow yourself to do nonlinear pre-processing to your data, you can make them extremely sophisticated. And in fact, when you look at things like deep neural networks, which are state-of-the-art models right now, and you actually look what's going on in this neural network, you can interpret the very last layer as a linear classifier, regressor, or whatever, and all the other stuff coming before as just some sort of sophisticated nonlinear data transformations. So in some sense, the most powerful models out there are built on exactly this idea. So linear regression is, on one hand, very simple, but on another hand, if you combine it with nonlinear data transformations, very powerful.
Do we need to realize by looking at the scatter plot that we should go for something like this? Like how someone comes up with a thing like this going with inverse?
Yeah, that's a great question. So, the old-fashioned way would be to have an expert tell you, I think you should be trying to predict 1 over miles per gallon. The modern way is to build a sophisticated predictor that's nonlinear and have the predictor learn from the data sets itself how to do this transformation, and that's exactly what the neural networks do. We have to wait a few more units until we get there, but that's a great question. So for now, we don't have a great way of knowing how to do the transformation, except for maybe some intuition. You'll get a chance to play with this on the next homework assignment, where I'll give you a model that's obviously nonlinear, but just by looking at it mathematically, you can see what it takes to make it linear, and then once it's linear, you can apply the standard procedures. Okay, all right. Any other